Welcome back, sophomores. This is our last new content. So this will be the last video that I post. I hope you've enjoyed them or that they've been helpful enough to you that you could learn what you needed to learn here. This is the end of momentum. You could say it's the end of the school year and we're running out of momentum. I know I certainly am. And so this is on with the last couple of details related to momentum. And then enjoy your summer. Here goes. This is a fact of physics. This is a universal law. Momentum is always conserved in every interaction that takes place between multiple objects. This is another universal law in physics and in the universe, that the total energy in a closed system is always conserved. But the kinetic energy in the system is not necessarily conserved. And for that reason, we classify interactions based on the amount of kinetic energy they have before and after the interaction. Here's the first example and the first way that we categorize interactions. There are three types that we'll talk about. The first is an elastic collision. In an elastic collision, the kinetic energy before the collision is approximately equal to the kinetic energy after the collision. So here's an example situation where we show that that's how it works out. Example, a good bounce. If it's a good bounce, then it's considered an elastic collision, and here's what that means numerically. First off, here's the interaction. There's a mass of 4 traveling at a speed of 3, headed towards a mass of 2 that is stationary. After the interaction, the mass of 4 is moving at 1, and we'll have to use conservation of momentum to figure out how fast the mass of 2 ends up going after the collision. So here's that work. The sum of the momentum before equals the sum of the momentum after. And we end up finding that the speed of mass 2 after the interaction is 4. To decide whether or not this was a good bounce or an elastic collision, we have to calculate the kinetic energy before and after the collision. So here's that. The kinetic energy before is half times the mass of 4, which was moving at 3, squared, plus half of 2 going 0 squared. And the after is half of 4 times 1 squared plus half of 2 times 4 squared. When we calculate both of those energies, we get 18 joules before and 2 plus 16 joules after, meaning that there's as much kinetic energy in the system before and after the collision. This is what makes it an elastic collision, where all of the kinetic energy in the system before the collision is still in the system afterwards, so no energy was lost to heat or friction. In an inelastic collision, the kinetic energy before is larger, typically by at least 10 to 15%, than the kinetic energy after the collision. This is a different way to say that the system loses kinetic energy during the interaction. Here's an example of that. A coupling, and basically any coupling that ever occurs, is an inelastic collision for reasons that we'll see shortly. Here is such a coupling. There's a mass of 3 and a mass of 1. The mass of 3 heads at a speed of 3 towards the stationary mass of 1, and they are merged or combined together to form a mass of 4 that moves at some unknown speed after the collision, or the coupling. We'll again use conservation of momentum to figure out how fast the mass moves after the interaction. So we'll say the sum of the momenta before equals the sum of the momenta afterward. In this case, m times v plus m times v equals m times v gives us that v is 2.25 units of speed. To determine that it's an inelastic collision in this case, we have to again calculate kinetic energy and then compare the before to the after. So here goes that. The before kinetic energy is half mv squared for the mass of 3 plus half mv squared for the mass of 1. And for after, the kinetic energy is half m and the recently calculated v squared. When we work those numbers out, we find that the energy before was 13.5 joules, but after it was only 10 and an eighth of a joule. Meaning that the before kinetic energy was greater than the after kinetic energy by about 30% in this case, meaning we would classify this interaction as an inelastic collision. And we could note that this is the amount of energy lost in the interaction. Here's the third type of interaction that we will classify. It's called an explosion, and it's where the after kinetic energy is bigger than the before kinetic energy. In an explosion, like this one, we typically have a single mass that ends up being more than one mass. So it's the opposite of a coupling. In a coupling, we have two or more objects that merge and become one. In an explosion, we have a single object that breaks into pieces. Here's our conservation of momentum calculation first to determine how fast this mass of 1 ends up going after the interaction. Again, momentum is conserved. 3 times 2 equals 1 times v plus 2 times 4. 6 equals v plus 8 gives us that the speed of this single block, this mass 1 block, ends up being 2 to the left, so negative 2. For the energy calculation, before we have half times 3 times 2 squared, and after we have half times 1 times negative 2 squared, and half times 2 times 4 squared, which gives us 6 joules before and 2 plus 16 joules afterward. 6 is far less than 18 joules, and so by our classification we notice that the energy has increased, the kinetic energy anyways, has increased from before to after. In this case the energy tripled. That was kinetic energy. And this means that 12 joules of non-kinetic energy must have been present in the system before the interaction. And what do we mean by non-kinetic energy? You'll recall we called this an explosion, and when you saw an explosion occur in a previous lesson video, I had loaded a spring, meaning I had given the system elastic potential energy. This was energy that was present in the system before the interaction, and that was not kinetic energy before the interaction took place. After the interaction took place, that elastic potential energy had turned into kinetic energy. And so when we say non-kinetic energy, we're really talking about any other kind of energy that could lead to motion. Often you might imagine that with the word explosion, we're talking about some chemical energy that's stored in the system before the explosion takes place, and that chemical energy turns into kinetic energy. Now that we've classified the different types of interactions in terms of the energy gained or lost in the interaction, we'll ask this question: what makes for a good bounce? And I would imagine that in your experience, a good bounce depends on the materials that are involved. So here are several pairs of materials that I would imagine you could guess at a ranking for most or least bouncy among these pairs of materials. A rubber ball on concrete is pretty good bounce. Glass on steel, you might imagine isn't so great, but if you take a marble, which is a glass sphere, and drop it onto a hard steel plate, it bounces pretty well. A golf ball on grass is not particularly elastic. A golf ball on pavement is pretty elastic, especially compared to something like grass. A golf ball on steel, I would imagine, is probably not quite as good as on pavement, but maybe I'm wrong. Styrofoam on steel is definitely not an elastic bounce. And steel on steel is quite elastic. I don't have it anymore, but I used to have a tube that we would drop a ball of many different materials into, and there was a steel plate on the bottom of it. And when we dropped a steel ball on the steel plate, typically it returned to about 98 to 99% of the drop height. Meaning if I dropped it from 100 centimeters high, typically it returned to somewhere between 98 and 99 centimeters. So this is an incredibly efficient energy exchanging pair of materials. If you drop a steel ball on a steel plate, it is incredibly elastic and doesn't lose much energy at all. I'd like to use that fact that steel on steel is a very elastic bounce to explain something about a toy that you've seen in my classroom or elsewhere. That toy is called a Newton's Cradle. Typically consists of 5 steel balls on strings, and it looks about like this. Here I've numbered those steel balls 1 through 5, and this is the question that I've asked students at this crossroads many times. If I throw ball number 1 hard toward ball number 2, why is it impossible to have both ball 4 and 5 pop up or jump up on the other side? I'm going to make 2 arguments for why it's physically impossible for more than just one ball to bounce up on the other side of the Newton's cradle if you throw a single ball towards the row of them. The first argument is a momentum argument. When you drop one ball or throw one ball towards this chain of hanging steel balls, there's a chain reaction that occurs at the speed of sound in steel. Here is that chain reaction broken into singular events that take place. Ball number 1 hits ball number 2. Ball number 1, since it has the same mass as ball number 2, comes to a complete stop because of conservation momentum, and ball number 2 takes off, going exactly as fast as ball number 1 had been going. So that's written in shorthand here. 1 hits 2, 1 stops, and 2 goes with equal speed. The next step in the sequence of events is that 2 hits 3, 2 stops, and 3 goes with equal speed. Then 3 hits 4, and 3 stops, 4 goes with equal speed. So at this moment, for example, if 1 hit 2 going a speed of v, by now 3 has hit 4, 3 has stopped, and 4 has all of the momentum, which is equal to the momentum that ball number 1 had in the first place. Then 4 hits 5 and 4 stops. 4 stops. That's the key here. That's the reason why, according to conservation momentum, ball number 4 cannot rise up if I throw ball number 1 hard at the entire row of these hanging steel balls in the Newton's cradle. 5 goes just as fast as 1 went, but 4 can't go anywhere because it has come to a stop, and there's no more momentum in the system to make it go. Now I'd like to make an energy argument as to why balls 4 and 5 can't take off if ball 1 hits the stack of these steel balls in Newton's cradle. Let's suppose, for our purposes, that the speed of ball 1 when it's about to hit the stack of them is 12. The units are arbitrary, they don't matter, so we'll just say the speed is 12. Let's also suppose that our goal is to have that single ball crash into the pile in the before, and in the after we're going to end up with 2 of them moving away with some speed so that 4 and 5 can pop up. If that's the goal, we still have to conserve momentum in the interaction. That means if ball 1 had a speed of 12, then the two balls that are coupled and leaving together would have to have, according to conservation of momentum, a speed of 6. If that's the case, we can calculate the energy required for those two balls to have a speed of 6. Here that goes. The kinetic energy before and after in this system, with a mass of 1 going 12 before and a mass of 2 going 6 after, looks like this. 1/2 mv squared before and after leads us to 72 joules versus 36 joules. This, by our definition from before, is a contradiction because the balls in a Newton's cradle are made of steel, which bounces incredibly elastically and does not lose 50% of its energy in the collision. These are the kinds of numbers for energy that we would expect in an inelastic collision, which this most definitely would not be because it involves steel balls. On the other hand, if we have one ball rise on the right side after the interaction, its speed would have to be 12, just like we said before, that ball number 5 rises or leaves the stack of them with equal speed to whatever ball number 1 had been launched into it with. In that case, we end up with the kinetic energy before that is equal to a kinetic energy after. This would mean that this is an elastic collision, which we know steel on steel is incredibly elastic. Here comes our final physics thought for the school year, and this is going to take you back to many times throughout the year when I tried as hard as I could in as many ways as I could to impress upon you, young drivers watching this video, the importance of paying close attention, driving safely, and anything having to do with a general awareness of exactly the power or energy that you hold in your hands when you're at the wheel. So here goes with that as a preface. From much earlier in the year, we know Newton's second law, it's F equals ma. We also know the definition of acceleration is delta v over delta t, so we can write, and have written in the past once in a while, that a force is m delta v over delta t. This was rearranged during our proof of conservation of momentum into F delta t equals m delta v. This is called the impulse momentum theorem, where the quantity on the left side of the equal sign, F delta t, is impulse, and the quantity on the right side is m delta v, which is a change in momentum. This is one way to change the momentum of a system, is to leave the mass constant but change the velocity. Formally, it's called the impulse momentum theorem, and more informally, I call it the rocket equation. This is related, among many other applications, to how exactly airbags save lives. We're going to look at some numbers in the context of the impulse momentum theorem involving two scenarios. The first one is, what if there is no airbag that is available to stop a person who is in a car accident? In this case, we're going to assume that there's a 60 kilogram torso. This is your upper body, chest area, and it is being stopped from a starting speed of 20 meters per second, which is about 45 miles an hour, in 5/1000ths of a second by running into a steering wheel. If this is the case, then from the impulse momentum theorem, we should be able to calculate the speed. We have a mass, we have a change in velocity, and we have a time. So we're going to find a force from our impulse momentum theorem. Question is, what force stops this torso or this person? Since F delta t equals m delta v, and we know the amount of time it takes this person to stop, their mass, and the change in velocity, which is their final speed minus their starting speed, we end up with a force of 240,000 newtons as a stopping force acting on this person's upper body. Just to give you some kind of an idea of what this would mean for the person who experiences it, this applies an additional pressure of 450 pounds per square inch on the person being stopped by such a steering wheel. That's 450 pounds on each square inch of the surface area. In scenario 2, we're going to imagine that this car, the vehicle, is equipped with an airbag, and the airbag stops the person. Now, your common sense or your sense of the world might indicate to you that the reason that airbags are helpful in instances like this is because they increase the stopping time. And they do that by increasing the stopping distance. Typically, an airbag might be a half a meter thick, and as it inflates and stops you, you're stopped over a distance of a half a meter instead of perhaps over half a centimeter by being pressed into the steering wheel or the dashboard, for example. In the airbag situation, it's the same 60-kilogram person being stopped from going 20 meters per second, but now in a much greater time, 5/100ths of a second, which still seems very fast, and it is if you've ever been in an accident, and I have. It all goes by very quickly because it is a very fast event. Regardless, in this case they run into an airbag, and so we can again calculate the force that stops the person who's involved in this accident. Again, we're using the impulse momentum theorem, which is that F delta t equals m delta v. I have at least once, and probably more like 100 times, heard students in past years refer to this as fat MAV, which I think is memorable enough to be worth maybe throwing into this video. So there you have it. If we calculate this force, we end up with 24,000 newtons, and it's negative because it's stopping the person. This still sounds like a very large force, and it is, but it can be survived because we're now not talking about several hundreds of pounds per square inch of pressure added to this person's chest, but instead 45 pounds per square inch of pressure on this person. This is why in car accidents where a person has an airbag that deploys or has a seat belt, sometimes they end up with bruising or broken ribs due to the seat belt. Sometimes they end up with a broken nose due to an impact with the airbag. But these kinds of pressures or forces are survivable, which is the benefit to airbags and generally how airbags save lives.